Thanks for having me. Today I'm going to talk about shifting left and how this plays into an emerging array of things that I regard as truths in software engineering. Much ink and many hours of conference talks have been spent discussing software engineering as a concept, and even asking the question, is this an engineering discipline at all? And in order for that to be the case, we need to look at what are the differences between software engineering or programming or computer science. If there really is an engineering discipline in here on its own, shouldn't there be fundamental truths? For instance, mechanical engineering is a distinct discipline from the more theoretical body, physics, and it has its own emergent formula and practices and understanding of the domain. If software engineering is actually an engineering discipline, shouldn't it be definable, and shouldn't there be truths that give us insights that are distinct from, say, theoretical results in computer science? And to that end, I'd like to make a few points. Nicole Forsgren, one of the authors of Accelerate, gave me a great quote one time. She said, "Accountants are still working out the details of their best practices, and accountants are mentioned in the Bible. Software engineering is only 50 years old. Give us a minute." And I think there's a lot of useful truth in that, right? It isn't an excuse, right? We do need to think about and work on and refine our best practices, right? But it does give us a little bit of a useful context to think about this, right? We are figuring it out. And similarly, I draw attention to Mary Shaw's talk, Progress Towards an Engineering Discipline, from a few years ago. She has in that talk a graph sort of like this that she uses to sort of suggest the development of engineering. And she uses in particular the building bridges and physics and mechanical engineering as an example, right? And she points out that humans built bridges for thousands of years before we actually got around to studying physics. And we formalized physics centuries ago, but we still didn't get bridge building down to a fully understood and packaged and reproducible problem until just recently. She talks about the Pennsylvania Department of Transportation having a software package for taking in descriptions of roadways and putting out, like, here is the design for that bridge, right? It is an entirely off-the-shelf push-button result, right? But it took thousands of years to get there, right? These things progress slowly. And I think similarly, our understanding of what is software engineering progresses slowly, but probably a little faster than the 1,000-year time frame. There is progress here. And in fact, the question of what is software engineering has, in my opinion, been answered many times with pretty identical underlying ideas. Probably Dave Parnas, the quote is a little unclear, somebody said, the multi-person development of multi-version programs, right? And this was circa 1970. This is 50 years ago. This goes back to almost as old as the term software engineering itself. And I think there's a lot of truth in that quote if you think about it and pull it apart. Russ Cox said just a couple years ago, software engineering is what happens to programming when you add time and other programmers. And I have pithily said, snarkily said, it's programming if clever is a compliment, and it's software engineering if clever is an accusation. And I think that when you sit with any of these, you can sort of identify that they are saying sort of the same thing, right? They are getting at the core idea that software engineering is distinct somehow because of ideas of time and change and collaboration. But if we accept that software engineering isn't programming, right? It is distinct in some fashion. Software engineering is the matter of producing solutions, probably via programming, and then keeping those solutions working over time in the face of changes to teams and staffing, priorities, product decisions, underlying technology, all of these things, right? And then we can start looking for the truths in this distinct from programming domain that may or may not emerge. And the first that I mention will come as no surprise to anyone that has ever seen me talk. It is Hiram's Law. With a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system are depended upon by somebody. Right? This is, to my mind, the first thermodynamic truth of software. This is what stands between your software system and change. And when you think about Hiram's Law as an analog for something like entropy, then it becomes clearer how we need to consider it, how we need to work with it. If you are going to change something eventually, then you are fighting that friction. You're fighting the Hiram's Law dependencies on the thing that you're trying to change. If you want to change something in the future, you might want to make it hard to depend upon that behavior in the present. And so we rely on things like non-determinism. Is a bit like grease in a software system, barring places where people rely upon that determinism. The example that I go to most often, and that's even in chapter 1 of the Software Engineering at Google book, is we talk about hash table iteration. Right? You know that if you put 5 elements into your hash table and then you iterate through the hash table, you're going to get them out in some order. But most people, certainly most programmers, don't know whether or not that order is actually guaranteed by the system to be stable for any given length of time, right? The Java JDK, for instance, specifically says we might change the order that hash tables are traversed in, right? But there's at the same time hundreds or thousands of places in a large code base that are actually dependent on the particular order that you visit entries in. And so we move in software systems like at Google, we move to worlds where we more aggressively mix up and shuffle the iteration order from hash table to hash table, from build to build, from run to run, so that it is hard or impossible for you to brittly and in a Hiram's Law fashion depend on the specific order that you happen to traverse those in. That said, Hiram's Law always applies. And we have actually encountered people who are using the fact that our hash tables are now non-deterministic ordering to use that as a crummy ability to shuffle the element, like they're doing it for random number generation. So we can't turn off the non-determinism without breaking them as well, right? Hiram's Law is always there. It is like entropy. You cannot beat it. You just need to plan for it. You need to think about it. You need to mitigate it. You need to minimize it. But this is not a talk about Hiram's Law. It's harder to pin down and get cited a little bit less, but I think there's another truth, a truth number 2, lurking in my favorite topic, time and change. Right? If Hiram's Law describes why change is hard, then we also need something to describe why change is necessary. This is wrapped up in what I refer to as sustainability. Over the expected lifespan of your code, be it your project, your code base, whatever, sustainable code is capable of changing everything that you ought to change safely. And this definition hides a ton of subtlety, including the important question of how long is your code going to live? How long does it need to be useful? And what level of cost you are willing to spend as an organization in the face of a rare event. But I think that this is very important and comes as a secondary to Hiram's Law, because Hiram's Law is describing why change is expensive. This is just describing that you need to plan for it. But this is very important. And I presented it as one of the first major principles of the book. And I will readily admit that we're still hunting for a concise way to really get at the truth that is hiding here. But I can say, if you're building your software with the hope that it's going to be for the long term, but you're pretending that nothing will ever have to change, that's a very bold bet. Good luck with that, right? Like, we live in a world where security vulnerabilities occur sort of pervasively everywhere. People, I feel like, don't have enough fear and respect for things like the speculative execution vulnerabilities that we discovered starting a couple years ago now and continuously are discovering in our very processors, right? If the compilers and programming languages are perfectly correct and all of your code works as intended, but there are security bugs lurking in the hardware, right? The mitigations on that are going to require substantive change in some level, right? Be it a compiler upgrade, a change to the language version, change to the operating system, or massive re-architecting of your entire system. And if you are betting that no change will ever be necessary, that you can build something and it will just last, that's dangerous. I think of this sort of in comparison to what we learned about tall buildings and earthquake zones, right? It feels right that you want strong, stable, sturdy. But it turns out that in the face of a shock, in the face of a necessary change, flexible is a far more reliable, far more safe option, right? You need the ability to react to things. And that's what I'm trying to get at here. Sustainable code. And a comparable third truth, will take up most of the rest of this talk, has emerged in the last 10 years. And I take no credit for it whatsoever. But since learning about it, I find it applicable sort of all over the place. I think there's a real depth here. And I love the idea of shifting left, doing things earlier in the developer workflow, in the software engineering workflow, is cheaper. And this terminology is based on this conceptualization of the developer workflow, which I actually do argue is an engineering workflow, since developer is really just developing code. Engineering is about the lifetime of that code. But regardless, at the beginning in the workflow, we look at things like bug reports or design proposals, and then that sort of flows into development and testing and code review, submission, integration tests, canary release, production, etc. And the term shift left, as far as I can tell, originated with the idea of shifting left on security. In the 90s and early 2000s, we were primarily, as an industry, distributing software that ran locally and didn't interact with your network. And it shifted, no pun intended, to being connected, right? It was an internet world. But as an industry, we didn't immediately realize the risks that came with connectivity, right? It is a different threat model to be connected to the vast anonymous internet. I remember as a youngster back in the late 90s thinking, boy, I sure do look forward to the day that we get all of these hackers to settle down and leave the internet as a good place. And I was young and naive. Anyway, most organizations sort of tacked on security at the end of the development process. You get your system to work in the way that it's intended to work, and then you're ready to ship it. And maybe if you're being very careful, you have someone check it for obvious holes, or someone poke at it in penetration test fashion. And the push to shift left was meant to move that like little add-on security thinking earlier in the developer workflow, earlier in the process. Test for security, code review with security in mind, discuss security starting in design docs. And the core idea is that a security bug found in live production code is far more expensive than one that is caught ahead of time, caught earlier. And that's not a binary thing, right? If you catch it in canary, you still have a fair amount of work ahead of you to track down what change was responsible and file bugs and rope in the team that put together that feature. But if you catch it in code review, then you know exactly what the issue is. And in fact, the developer that is in the process of potentially introducing this vulnerability, potentially introducing this bug, has already paged in what their goals were, what their thinking is, right? That is going to be a much cheaper place to resolve the issue, so long as we discover it earlier, so long as we shift left. And if you catch it in design, then it's even cheaper still, right? No code needs to be rewritten. Bad, risky features can be squished early. Languages like Rust are going to great lengths to shift left on certain security risky development practices which pushes the detection of bugs that involve object lifetimes and memory sharing so far to the left that they can't even generally make it to code review. And that, I think, is actually the strongest criticism I've seen to the shift-left model. It makes more work for developers. But this is true, and it gets back to the distinction from a few minutes ago. Programming or development is not the same as software engineering. Goals and best practices are going to be different. When you consider that some programs need to last only for a few minutes and others need to last and be usefully changed for decades, it seems bizarre that people don't draw a distinction between these domains, or at least most people don't. But people like me do, and the message that we've had for 40 or 50 years is the same. Time is the hard part here, people, right? The part that matters, the part that makes things different. Time is what separates programming from software engineering. Languages, going back a step, languages like Python are popular because they make programming fun again. Things are quick and smooth and expressive and easy, but they're also pretty solidly recognized as being bad languages for long-lasting large team projects. They are programming languages, not software engineering languages. Most languages these days are trying to be both, or like Python, are pretty explicitly only programming. Someday, I personally hope that we'll see something that is built to prioritize and handle the long-term case. I don't think we've seen it yet. I think we've found languages that happen to be okay for the long-term case, but that's not really what they're quite optimizing for. Most languages do long-term by virtue of nothing changes, which, like I said before, is building a very, very brittle building. Back to shifting left. The same shift-left model applies to bugs of all sorts, not just security issues. Or maybe more accurately, in the hands of a sufficiently powerful attacker, all bugs are security bugs, and there isn't much value in conceptualizing them differently, right? And so, like, you could sketch out a totally made-up graph, like the estimated cost of, like, how bad is it to discover a bug at this point in the cycle. And from a certain point of view, the whole reason that we have testing is to catch bugs before they go to production. Tests are our oracle for, would this change be good, or is trunk still good, right? If we cut a release right now and push it to production, is that going to be okay? We even talk dismissively of testing in production. But the fact that we immediately go from this idea of production fitness and testing means, like, I think that there's parallels that we can draw there. Drawing connections between code in production and code pre-release. Like, for instance, I've said for years that my product is Google's code base, right? I have a whole fitness model and acceptance criteria for just getting to the point that it commits, and then I'm done with it. But my favorite of these sort of across the developer workflow, across the engineering workflow connections is this claim. Continuous integration systems like Travis or Jenkins or whatever you have in-house that's running your tests constantly and doing the build constantly and telling you whether or not our estimate is that the build and tests currently pass. These are the left shift of your production alerting systems, the systems that you use to trigger alerts and pages for sysadmins or SREs to say, the system is unhealthy or the system is down. And I don't just mean this in a simplistic fashion, right? This is a deep connection that you can't unsee. If you're anything like me, you'll be spotting equivalences in this idea for weeks to come. Consider, your alerting system does nothing if you aren't exporting stats and metrics for it to monitor, right? You can't alert if there's no signals to be keeping track of whether those signals are good. You want your production systems to track basic things like latency and queries per second and task restarts. But you'll usually, almost always, I would assume, have more domain-specific metrics based on the application logic. That'll be something like data throughput for a storage system or average dwell time for a video site. When the exported metrics, either the general ones or the product-specific ones, gathered and aggregated fall out of some acceptable range, then you fire off a page to whoever is on call, your SRE or your developers, as an early warning for impending production failure and maybe user visible outage. If those pages go off regularly because a threshold was chosen poorly, then in SRE terminology, we're failing because of a bad rule-based alert, right? I picked a threshold. It wasn't actually correlated with system health particularly. I fired off too many alerts. In the end, we have to adjust that threshold. In testing parlance, that's a brittle test, right? It's firing for reasons that aren't actually actionable. Similarly, if pages go off regularly but are just transient, that's a flaky test, right? Those are completely comparable. I will go deeper. Every single assertion and invariant that you have in your test suite could be exported and monitored in your alerting system. But we specifically don't do that because all of those bugs, all of the places where the invariants don't hold, have already been caught earlier in the workflow. But if you wanted, for some reason, to run a big project with no unit tests, you could, in theory, add all of the exact same assertions to your production alerting frameworks. It's just going to be higher risk and more expensive to catch those bugs at that point because it's so much further to the right in the workflow, right? We've already started to run some of this code in production. So if the alert goes off now, it's going to be an SRE's job to decide, oh, something's bad, roll back to a safer release version and file bugs. Then we have to investigate what those bugs are, et cetera, et cetera. All of that remediation is vastly more expensive than a developer, even before they submit, running the tests and the same invariant going off, right? It's the same thing. Another view. The highest value alerts, the things that your production folks will say, this is necessary, are the end-to-end probe that mimics user behavior and gives you an actual ground truth for, is the system up? Most alerts are much more granular than that, right? They're measuring resource consumption and your random per system assortment of metrics, right? Everything else other than that end-to-end probe is a proxy for not is the system up, but is the system healthy? A prediction of whether the site is going to stay up in a few minutes. And this is exactly the comparison between an end-to-end integration test and a test suite of unit tests. We can draw many such parallels between these two domains. So when I'm saying CI is alerting, I don't mean if you squint, you can see some parallels. I actually think that most of our understanding and best practices in one domain carries over into the other. Put another way, what we're optimizing for is product fitness, right? In a web, cloud, DevOps sort of world, this largely means we can provide value for users from what is deployed to production. If the system goes down or there are bugs that are preventing us from providing that value, that's bad. And the thing that tells us, are we providing value, are these end-to-end probes that I mentioned before. Those probers constantly monitor whether the system is up and give us a chance to react as quickly as possible if something goes wrong. That is the gold standard for cloud systems that are dealing with real-time user traffic. But more fine-grained monitoring and alerting gives us proxies for the details on the health of the system. Not is it down, but is it heading toward down? And canary releases often use the same monitoring system to ask, if we deployed this version instead, would system health and fitness drop? End-to-end system and integration tests are the very same thing as canaries, perhaps with lower fidelity or more controlled dependencies, but they're often even monitoring the same sort of outcomes. Less end-to-end, like more constrained integration tests, because it's a spectrum, are smaller and cheaper and, like I said, more constrained, but they will also have slightly lower fidelity, right? It's possible for bugs to slip through your integration tests and need to be caught by end-to-end tests or canary. Unit tests are cheaper still, often cheap enough to run pre-submit, but they're still just predicting the same thing, right? If this was committed and a release was produced and that release went to production, would system fitness drop? And for every invariant, for every assertion, every unit test is a direct proxy of those application-specific metrics like dwell time or throughput, right, that we monitor and alert on. Your CI system is complaining that your tests don't pass, and that is the exact same thing as those production alerts firing. It's the same logic as the alerting system. It's just earlier in the workflow. And now, with this insight in place, given that SRE has had a high-pressure need to figure out how to manage alerts and the best practices for production management, suddenly, when we're talking about just testing, we have this massive available insight and jump forward, right? We draw these sorts of parallels. We read the SRE practices that are published, and then we can see how to apply them here earlier in the workflow. So for example, SRE will tell you that the goal is not 100% uptime. Having a site with 100% uptime is very difficult, very expensive, and requires you to be extraordinarily risk averse. And worse, it usually doesn't matter. Most consumers don't have remotely reliable an internet connection so that they could detect the difference between 100% uptime and 99.99% uptime. Right? Dropping for a few seconds at a time or a minute once in a while isn't likely to be noticeable for most services. It's totally lost in the noise of your users' internet access and local hardware and software issues. What we want instead is to conceptualize not 100% uptime as the goal, but your error budget, right? 99.9% uptime is the goal, right? And then you use that 0.1% downtime as literally a resource to be spent, right? If we want to stay within that target, how fast do we need to react when we're not up? If we are, over the last 6 months, running significantly more reliable than that, then that suggests we can put out releases more aggressively, we can take some risks, we can spend that budget. And if we have overspent, then we need to throttle back, right? Be very conservative in our releases to not overspend, right? To stay within budget. So if we have in mind that alerting, which is what we would use to measure our actual uptime and our error budget, is the same thing as your CI system, then this suggests that CI is always green might itself not be the right goal. What we want is to mitigate risks and be able to return CI to green rapidly. And as it turns out, most policies and most places regarding your CI systems sort of match that behavior. If we were aiming for 100% CI green, then rules about pre-submit testing and syncing would usually be quite different. That is, today, there's usually a race between the point where you kick off pre-submit tests and where you submit. So long as nobody modifies the files in your change, you can usually submit. But that isn't actually proof that their change and yours are compatible. But this is still working as intended. This is working correctly. If we had to sync and retest just because someone else committed somewhere in the repo, then that means over time that the average maximum number of commits per day is 24 hours divided by the average time it takes to sync and retest. This might be okay for a team of 2 or 5 or 10, but it certainly does not scale up to 10,000 developers. But we're not fully invested in the error budget model for CI. SRE will tell you that there are some times that you get a page and there isn't actually anything wrong. Some brittle alert fired. You take a look, everything seems fine, you silence the alert. Alerting systems, as I understand it, tend to have this sort of acknowledge and silence button for just this purpose. But we generally don't have the same for continuous integration systems, right? If someone commits a perfectly correct change that breaks your brittle test, the CI system is going to yell at you. And in many organizations, that commit is going to get rolled back. And that might be the right default behavior. But what if we could spot quickly or know ahead of time that the change is right and the test is wrong? Why don't our CI systems have this sort of ack and silence button for those tests, right? We file a bug, handle it in the next sprint by either re-enabling or deleting the brittle test after having updated it to not be so brittle. I find this whole model to be really illuminating. Everything that we're doing is optimizing for product fitness. All that matters is fitness in the release. Everything else in the engineering workflow is an attempt to improve fitness cheaply, rapidly, reliably, while acknowledging that we're aiming for the multi-person production of multi-version programs. The earlier that we resolve an issue, the cheaper, but the more abstract the fix and the lower fidelity the solution. So thus, we layer best practices and we use them as a defense in depth strategy. And that is okay, because in the aggregate, when we listen to the full suite of best practices, then we're pretty sure that the aggregate power and fidelity means that your fitness is going to go up for a reasonable cost. And you see this when you look back at this graph, right? Your end-to-end probers, this is the gold standard. Like I said, is the system still up, right? Can we provide value? And your simpler alerts are lower fidelity. Is the system still healthy? Will it be up in a few minutes? But even if your simpler alerts go off, that isn't actually proof that you're about to go down, right? There's a fidelity question in there. And your canary release is the question, if we release this, will the system still be good? Or will the value go up? Your integration tests are lower fidelity canary releases. Post-submit CI is lower fidelity than that. If we cut a release from now, from trunk at this point, is the system still good? Code review, etc. All of these things, right? The important piece to note here is that every time that we move left on this scale, detection and mitigation of a given bug is cheaper. But at the same time, the signals that are indicating, yes, your code at the moment is fine, go to the next stage, also have dwindling fidelity, right? Because every layer of this is a proxy. Just because you passed pre-submit tests and code review isn't proof that it's going to be okay in production. It's a proxy. That's why we have integration tests. If we had perfect code review and unit tests, most of these things would go away. But we're humans and software is messy. It's never going to be perfect, right? We need to acknowledge that these are proxies. And thus we focus on making sure that our proxies are both high fidelity and actionable at every step in the workflow. And this model, I think, cuts to the core of why shift left seems so potent and broadly applicable. Why it's arguably a fundamental truth in software engineering. But the more nuanced point is that it ties together this interplay between cost and fidelity, cost and detection. Shifting left is in your engineering workflow is trading specifically between risk and cost for a given bug and the likelihood that there might be false positives or the overall fidelity of how sure are you at this point that your release would actually be good. And everything that I've seen that is part of a good modern software engineering workflow seems to fit this model. And thus, we can start to generalize a little bit. I would argue that in the software engineering workflow, everything in this workflow is about communication within your team or improving product fitness or both. Anything in the workflow that requires broadcast one-to-end communication that's going to your whole organization, not just your team, is going to be a risk, right? Like those things don't scale well. If we have to make announcements of, oh, this behavior is changing, please everyone test your code. Oh, this behavior is changing, please everyone make this update. Those are going to be scaling problems and risks in the workflow. Shifting any given process, shifting any given piece of detection, shifting any given where can we find this bug to the right is eventually going to be a problem. Those costs often grow superlinearly with the size of the team that's impacted by those. And I suspect that if you look at process changes in your career that really fail spectacularly, it probably violates this one in particular. We had internally at Google an issue for a number of years where we wanted to make sure that most developers could sync to head and have something that worked nicely. So we sort of drew a line across the components and subsystems that effectively everyone depended on, and tried to specifically give the developers on those teams more freedom to make their commits and have someone further down the line catch when they broke the build. And that is, in retrospect, we shifted a little bit of the CI in the workflow further right. And this caused a lot of complaint and consternation, right? In retrospect, to me, it's perfectly obvious why this turned out to not scale well and to be sort of a burden. I would also say that arguments of the form, we already have something in the workflow that solves this, so we don't need something else, should be ignored if there's a difference in how early that is, right? It's perfectly okay to have multiple things in the workflow that are catching bugs, right? Static analysis and code review and CI and dynamic analysis and fuzzing and all of these things are all there to find bugs, and they are good at finding different types of bugs. And they happen at different levels in the workflow and at different costs, right? The more of those that you can pack in earlier in the workflow to discover the majority of your bugs early and cheap means you can spend less on the overall resource costs for your integration tests. And most of your canaries are going to succeed, things like that. This all suggests to me that we've hit upon something substantive here, and that the shift-left model is perhaps powerful enough to land in this bucket of emerging truths for software engineering as an engineering discipline. And so we go back to this big question: is software engineering even a real discipline? And I have to give that a qualified yes. Right? It was in vogue for a long while to ask this question, but I think it's increasingly silly. Yes, there is a real discipline lurking here. It is a new field, software engineering, as these things go. Mechanical engineering, draws its roots from our earliest bridge building thousands of years ago. Software engineering is so much newer than all of that. I have been a programmer for about half as long as the term software engineering has existed. I'm not that old. So yes, as a discipline, as an industry, we're taking some shaky steps to get our footing, but the path is becoming increasingly clear. There's definitely a discipline here. There is a clear study here, right? It is the application of computer science and programming methodologies, but scaled up for many people and over a long time frame. A physicist can answer the question of whether a bridge in theory will hold a given weight, but an engineer is going to be better at answering whether that bridge will hold the weight after 50 years of weather and wear. I think the same delineation applies in software. And just as our more formal and more advanced engineering colleagues have their own emergent knowledge and practices, we do too. Hiram's law governs how easy things can be when we try to change things. Our definition of sustainable software helps motivate the need for the capability of change, building that flexible building, not the brittle ones. Not motivating change for change's sake, but having enough malleability and enough practice to be able to change when it matters, when that new security bug comes out, or just when your product plans and product requirements change. And when studying how we practice software engineering, I think it's important to keep in mind this additional truth of the shift-left trade-off between cost and fidelity. And I'm sure that there are many other truths out there and better ways to characterize and understand these, but I think these help provide a mindset and a lens through which we can see the ways that modern software practice is evolving, not purely as a change in fashion, right? This is not just a buzzword. There's a truth in here, but as a move toward a better understood practice of software engineering as a discipline. And with that, I think we move to questions.